Have you ever looked up at the night sky and wondered what's out there? Beyond the stars we can see with our own eyes. For thousands of years, humanity has been asking that same question. We built bigger and better telescopes on mountaintops, peering into the cosmic darkness. But we hit a wall, a shimmering, blurry wall that we couldn't see past. That wall is Earth's atmosphere. And that's why we sent telescopes into space. Today, we're going to dive into exactly why space telescopes like Hubble and the James Webb can see farther and clearer than any telescope stuck here on the ground. It's a story of science, engineering, and our relentless desire to know our place in the universe. So, first things first, let's talk about our atmosphere. It's great, right? It gives us air to breathe, protects us from harmful radiation, and keeps the planet at a cozy temperature. We literally wouldn't be here without it. But for an astronomer, it's a bit of a nightmare. Imagine you're at the bottom of a swimming pool, trying to read a newspaper that someone is holding up above the water. The words would be all wavy and distorted, right? The light from the newspaper has to travel through the moving, churning water to reach your eyes, and it gets all jumbled up. That's almost exactly what Earth's atmosphere does to starlight. Our atmosphere is a turbulent ocean of air. There are layers of different temperatures and densities, and it's all constantly swirling around. As the faint light from a distant galaxy travels millions or even billions of years to reach us, it hits the top of our atmosphere, and in that last tiny fraction of a second, its perfect path gets bent and scattered. This is what astronomers call atmospheric distortion. To us on the ground, it's what makes stars twinkle. It might look pretty, but for a telescope trying to capture a sharp image, it's like trying to take a crystal clear photo through a heat haze shimmering off hot pavement. The image gets blurred, and a lot of the fine detail is lost forever. By placing a telescope in space, we completely bypass this problem. Up there, in the vacuum of space, there's no air, there's no swimming pool to look through. The light from a distant star travels unimpeded right up to the telescope's mirror. The result? Images that are incredibly sharp and detailed, far beyond what's possible from Earth. It's the difference between looking through a frosted window and a perfectly clean pane of glass. This is why the Hubble Space Telescope was such a game changer. When it sent back its first images, astronomers were stunned by the clarity. They could see individual stars in other galaxies, something that was just a fuzzy blur from the ground. It revealed the universe in a detail no one had ever witnessed before. But it's not just about blurriness. Our atmosphere also acts like a giant filter. It blocks out most types of light from ever reaching the ground. You see, the light we can see with our eyes, the visible spectrum, is just a tiny, tiny sliver of all the light that exists in the universe. There's a whole spectrum of light called the electromagnetic spectrum, which includes things like gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves. Our atmosphere is very good at blocking most of these. It stops almost all gamma rays, X-rays, and most ultraviolet light. This is great for us, because that stuff is harmful. But it is not so great for astronomers, because many of the most fascinating and energetic events in the universe, like black holes gobbling up stars, or the birth of new stars, inside dusty nebulas, shine brightest in these types of light. And then there's infrared light. Infrared is basically heat radiation. Everything in the universe that has some warmth emits infrared light, including you, me, and even the telescope itself. A lot of infrared light is absorbed by water vapor and other molecules in our atmosphere. This is a huge problem, because some of the most important things astronomers want to see are only visible in infrared. Why is infrared so important? Well, think about the early universe. The universe is expanding, and as it expands, it stretches the light traveling through it. Light that started out as visible or ultraviolet from the very first galaxies, billions of years ago, has been stretched so much that by the time it reaches us, it's now in the infrared part of the spectrum. So, if you want to see the first stars and galaxies forming after the Big Bang, you need an infrared telescope. And if you want to see them clearly, you need that telescope to be in space, away from our atmosphere that blocks and glows in infrared. This is the whole reason we built the James Webb Space Telescope. It is a specialized infrared observatory. Not only is it in space, but it's also incredibly cold. It has a giant sunshield the size of a tennis court to block heat from the sun, Earth, and Moon. Why? Because if the telescope itself were warm, its own infrared glow would blind it, like trying to take a picture of a candle while standing inside a bonfire. By being in space and being ice cold, Webb can detect the faint, ancient infrared light from the dawn of time. It's looking back over 13.5 billion years to see the baby pictures of our universe. That is something that is fundamentally impossible to do from the ground, no matter how big your telescope is. Now, you might be thinking, what about those huge telescopes on mountaintops in Hawaii or Chile? Are they useless? Absolutely not. Ground-based telescopes are still incredibly important. For one, they are much, much bigger than anything we can launch into space, and bigger means you can collect more light. Think of a telescope's mirror like a bucket collecting rainwater. The bigger the bucket, the more rain you can collect in a certain amount of time. Similarly, the bigger a telescope's mirror, the more light it can gather from faint objects. Today's largest ground telescopes have mirrors over 30 feet across, and we're building ones that'll be over 100 feet across. Compare that to Hubble's 8-foot mirror, or Webb's 21-foot mirror. Ground-based telescopes can gather so much light that they can study faint objects in ways space telescopes can't. And plus, they're way cheaper to build, and you can upgrade them with new instruments and technology much more easily. You can just drive up the mountain. You don't need a multi-billion-dollar space mission. And scientists have gotten really clever at fighting back against the atmosphere. They've developed a technology called adaptive optics. It's amazing. Basically, they shine a laser up into the sky to create an artificial guide star. A computer measures how the atmosphere is distorting the light from this laser spot, thousands of times per second. It then uses that information to rapidly change the shape of a small, flexible mirror in the telescope's light path. This flexible mirror deforms itself in just the right way to cancel out the atmospheric blurring. It's like if you knew exactly how the water in the swimming pool was moving. You could wiggle the newspaper in just the right way to make the words appear clear to the person at the bottom. Adaptive optics can produce images from the ground that are almost as sharp as what Hubble can achieve, which is a mind-boggling feat of engineering. But even with adaptive optics, ground telescopes can't solve the other problem. The atmosphere as a filter. They still can't see the X-rays. Most of the ultraviolet, or the specific wavelengths of infrared that are blocked. For that, you absolutely have to go to space. So, it's not really a competition between ground and space. They're teammates, each with their own unique strengths. Space telescopes give us an incredibly clear, unfiltered view of the universe across the entire spectrum of light. They can see the very first galaxies and peer into the hearts of dusty star-forming regions. Ground-based telescopes, with their enormous mirrors and adaptive optics, can gather immense amounts of light to study faint objects in incredible detail, in the wavelengths that do make it to the ground. Often, a discovery made by a space telescope will be followed up by large ground telescopes for more detailed study, and vice versa. In the end, putting telescopes in space isn't just about seeing further. It's about seeing clearer and seeing the invisible. It's about removing the shimmering veil of our atmosphere so we can witness the cosmos as it truly is. From Hubble's stunning portraits of cosmic masterpieces to Webb's journey back to the dawn of time, space telescopes have fundamentally changed our understanding of the universe. They've answered age-old questions and, more importantly, have shown us that there are new, more profound questions waiting to be asked. And that spirit of discovery is what drives us to keep looking up. Thanks so much for watching. If you enjoyed this journey into cosmic observation, don't forget to like this video and subscribe for more deep dives into science and space. Let us know in the comments what you'd like to see us explain next. See you in the next one.